Hello, this video is going to be on section 6.6, which is titled Function Operations, and there are actually two learning targets for the section. The first one is to add, subtract, multiply, or divide functions, and the second one is to find the composite of two functions. Now, when I say functions in both of these targets, one can look like f of x, and the other could be g of x. So if we're trying to find the composite of two functions, or if you're trying to add, subtract, multiply, or divide, these are what the symbols for two different functions look like. One could be f of x and the other is g of x. Okay, so if we look at how to add two different functions, and we're looking at the difference between f of x and g of x, a few different notations that I may introduce or show is that we have f plus g of x, since you are taking the f and the g and you are adding them, of f of x. Or I may also write it like f of x plus g of x. Whatever two functions you have, whatever variables are in there, you are able to add all of them together in a single expression. Same thing goes for subtraction. F minus g of x, or if you write them out separately, where one function subtracted the other, it can become f of x minus g of x. So whatever two functions you may have, you can add or subtract them exactly how they are, and we'll go over what it'll look like in an example. Then the next two are multiply and divide, and exactly how you think it would be, since these are plus and minus. We have f times g of x, or it may look like f of x times g of x. Whatever functions you have, you can multiply them together exactly how it is, and whatever you get, you get. And then same thing for division. F divided by g of x, or you may see it as f of x on top divided by g of x is on the bottom. Now there is one extra criteria for division that you have to keep in mind. Since you are dividing them, you cannot divide by the 0, so this is as long as g of x is not 0. So if it is anything but 0 of a function, then you can divide it. It could be 1, 2, 3, x, 14x squared plus 7, I don't know, anything as long as it's not 0. So these are the more important notations that I'm wanting you to be concerned about. I will very rarely write this, but you may see this either in the book, on the test, in the ACT especially, you may see something like this. But in my class at least, you will see something mainly similar to what's on the right side. Okay, so let's say we have two different functions where f of x is 4x plus 7 and g of x is the square root of x plus 6. And we want to find what f plus g of x is equal to. Now again, I would prefer to write it as f of x plus g of x. So we're going to take our f of x function, which is 4x plus 7, and add it to the square root of x plus x. Now the only terms that you can combine in this expression are your x's. So we have 4x and a positive x, which can be combined, and it's 5x, and we have plus the square root of x and plus 7. I prefer to write my numbers last and all of my x's first, and this is what f of x plus g of x simplifies to. There's nothing else you can combine. It's exactly like that the way it is. Then f minus g of x. You still set it up exactly the same way. You take your f of x function and subtract your g of x. So 4x plus 7 minus, and make sure you have a parentheses around this. I do tend to get in the habit of writing parentheses around both of my functions regardless, but it's very important that you do it over with a subtraction problem, because when you are subtracting, you distribute this negative into here and here. So it is no longer minus square root of x plus x. If you distribute the negative, it becomes negative square root of x minus x. So now when you are combining your like terms, you're combining a 4x and a negative x, which gives you a 3x. Then it is minus square root of x plus 7. So f minus g is a lot different than f plus g, because we have a 3x and a 5x, and these are plus or minus. The 7s are the same, but just line up your equations next to each other. Whatever operation is between them, whether it's minus or plus, just follow those exact same rules that you're used to, and you'll get the answer that you need. Okay, now if we're using multiply and divide, it's still the exact same way setting it up. F of x times g of x, and my f of x function in this example is x squared minus 9, and this is being multiplied with x plus 3. Now since we have two binomials being multiplied, we're going to have to FOIL. And if we multiply the first, x squared times x gives me x cubed. The outside is 3 times x squared. Squared, sorry, not cubed. Then the inside is negative 9x. And last is negative 9 times 3, which is negative 27. There's nothing I can reduce because all of my terms are different. A cube, a squared, an x, and a number. So this is f times g of x. Okay? Now same thing setting up with f divided by g of x. You take your f of x on top, and you divide it by your g of x on bottom. Okay, now in this case we are able to factor out some things and cancel them out. What you look for when you factor is at the top is a difference of perfect squares. You can take the square root of the first term and the square root of the second term, get whole numbers, perfect squares, and there is a difference between them. So the top factors to be x plus 3 and x minus 3, since the first term is the square root of the first one and the second term is the square root of the second one. One is plus, one is minus. Carry over your denominator, and the term that's in common that we can cancel out on top and bottom is x minus 3, x minus 3. So my answer to f divided by g of x is x plus 3. Okay, since my g of x wasn't a 0, I am able to divide. It was an x plus 3. So factor and cancel to simplify all the way to get your x plus 3. Okay, so now moving on to the portion that my second learning target was talking about, and that's finding composite functions. A composite function is if you are taking one function and plugging it into another function. And when I mean that is you still have your f of x and your g of x as two different functions. But let's say if we want to plug our f of x into our g of x, it is now going to read like g of f of x. Now it looks a little different as an O, so another notation that I may use looks like this. I'm going to pick a different color. So we have g on the outside, and on the inside of my parentheses I have an f of x. So I have an f of x inside my g of x function. Now if we look at the first this example, two different functions, an f of x is x minus 5 and a g of x is x squared. So if we're trying to find g of f of negative 3, what we're actually doing is we are evaluating f at negative 3 first and then plugging it into our g function. So if we take our f of x and wherever we see an x, we plug in a negative 3. This means that f of negative 3 is equal to negative 8. Now we're going to then take this and plug it into our g of x function to get g of f of negative 3. So g of f of negative 3 means we plug in a negative 8, since this is what we solved for, and negative 8 squared is equal to 64. Okay, if you would prefer, there is another way to do it, which I'm going to show you in this example, where we can actually take the f of x function and plug this entire thing into our g of x, wherever we see an x, and then plug in a 3 from there. So if we do it that way, going backwards, plugging in the g into the f of x, that means we have our f of x function, and wherever we see an x, we're going to plug in our g of x. So for every x, we're going to do an x squared, and this is minus 5. So this is the function f of g of x. Now if we want to evaluate it at negative 3, f of g of negative 3, that means wherever we see an x, we plug in a negative 3. And then we subtract 5. So negative 3 squared is 9. and 9 minus 5 is equal to 4. So these two numbers are not the same. Even though we're both evaluating at -3, this first one we're taking our f of x and plugging it into the g of x, and then the last one we're taking our g of x and plugging it into our f of x. They're kind of backwards, so we do get a different answer. Okay? I will show some more examples if you need more clarification on composite functions. I'm not entirely sure if you've seen this in any other classes or if this is brand new, but if it is, it can be kind of a confusing concept. But once you get the hang of it on seeing which one to plug in first, my always word of advice is whatever function you see last, that is what you plug into the one in the beginning. So this example, we took f of x, plugged into the g of x because f was the second one mentioned. Then this one, g was the second one mentioned, so we plugged it into our f. Okay? Thank you.